Okay, let's take a look at a few examples from your last homework assignment 5.4. I only gave you 5 problems to look at it, so it shouldn't be too bad. I'm going to look at a few just kind of different ones. Let's start with number 7. And the thing about the fundamental theorem of calculus that I've seen with my students is that you just have to trust it. You just have to believe that it's true, even though it seems like it's a very difficult problem. We have the integral from 0 to x, or the square root of 1 plus 2t dt, and we want to find, in this case, we want to find the derivative. We want to find g prime of x. Well, the instinct, again, to find the derivative is that you first want to take the antiderivative of this thing and then take the derivative of that. But you can just use the fundamental theorem of calculus, which says that the derivative is the inverse of the integral. In other words, you're just going to get back 1 plus 2x. Just replace the t with an x in that function. It's just that easy, my friends. It's just that easy. You just have to trust the fundamental theorem of calculus. It's a fantastic tool. It took a long time to develop. You might as well reap its benefits. And it doesn't matter that there's a 0 down there. For example, in number 8, where we have g of x is equal to the integral from 1 to x, natural log of t dt. Well, g prime of x here is just going to be the natural log of x. Again, as long as, here's the key here for these first two problems, as long as we have a constant here, whether it's 0 or 1 or 5 or 11, it doesn't matter, constant here, and we also have to have a just the variable x here. Then you just run that fundamental theorem of calculus. Just basically take this function, in this case natural log of t, and replace that t with an x. Okay? Now they can get a little bit trickier. For example, number 10, let's try this one here. Number 10, you have the integral from x to 10. We have capital F of x is the integral from x to 10 of the tangent of theta d theta. Alright, so it doesn't matter what this variable theta is here. Again, the integration variable is a dummy variable. Well, what we can say is that this is equal to the negative. Remember, we can reverse the limits of integration by changing the sign. So we can say this is the integral, the negative integral of 10 to x of the tangent of theta d theta. And now to find the derivative, f prime of x, well, now we can use the fundamental theorem of calculus. It'll be the negative of the tangent of x. Again, we had the constant here, just the x variable there, so the fundamental theorem of calculus is in play. Now, there is a situation where you have to do a little bit more than just the fundamental theorem of calculus, and that is when the top limit of integration is not an actual, it's not just in terms of x. For example, number 11, where you have the function h of x, and it's equal to the integral from 2 to 1 over x of the arc tangent of, what's this going to be, t dt. Well, here what we're going to do is we're going to have to do actually a chain rule here. If I let u equal 1 over x, then h of x is actually a function of u. It's h of u of x. And so, what's the derivative h prime of x going to be? Well, it's going to be h prime of u of x times the derivative of what's inside u prime of x. So I can think of h of x as being the integral from 2 to u arctangent of t dt, where again u is a function of x. And so h prime of x is going to be, first of all, the derivative with respect to u. Well, now with respect to u, we just have a single variable up here, so we can use the fundamental theorem of calculus. We can just say that's going to be the arctangent of u. But then I have to multiply that times u prime of x right here. Well, u is 1 over x, which of course is the same as x to the negative 1. The derivative of that then is going to be negative x to the negative 2. So that's u prime of x. Now the last thing I want to do is replace u with what it's equal to. It's equal to 1 over x. So we have the arctangent of 1 over x times the derivative, which is just negative x to the negative 2. In other words, to use the fundamental theorem of calculus, when this upper limit of integration is not just a variable, it's actually a function of the variable, you're going to rewrite the function with that variable, in this case, well, rewrite the function with this in place of the variable times the derivative of what's inside. And it's just an application of the chain rule with the fundamental theorem of calculus. We'll try one more of those. For example, number 13, where we have y and it's equal to the integral from 3 to the square root of x, the cosine of t over t dt, cosine of t over t dt. So we want to find, in this case, dy dx, but again, we're going to think of this as a chain rule here. So what I'm going to do is I'm going to rewrite my function I'm integrating, only in place of t, I'm going to put the square root of x, because that's what's up here, and then I multiply that times the derivative of the square root of x. So the square root of x is the same as x to the 1/2. The derivative of that is 1/2 x to the negative 1/2. So what do we have here? We could simplify this a little bit. We got the cosine of the square root of x divided by 2 square root of x times the square root of x. This square root of x right here comes down in there, and the 2 is down there. So we got the cosine of the square root of x over 2x. That's all there is to it. Now, one more example I want to look at. I think maybe one, maybe two more. No, I think, well, let's go ahead and set up 16, and maybe we'll take a gander at 17 as well. Number 16, you have that y is equal to the integral from the sine of x to the cosine of x of 1 plus v squared to the 10th dv. Now, this one looks mean, but if we follow the hint given in number 15, we can split this integral up. We can say this is the integral from the sine of x to 0 of 1 plus v squared to the 10th dv plus the integral from 0 to the cosine of x, 1 plus v squared to the 10th dv. Now I want to say then, I want to flip this one around here, so I have the constant in the lower limit of integration and the function in the upper limit of integration. So I'll make that a negative 0 to sine of x, 1 plus v squared to the 10th dv plus my integral from 0 to cosine of x, 1 plus v squared to the 10th dv. And now I'm ready to find dy dx. X is my variable. And what I'm going to do for this first one here, the fundamental theorem of calculus, I'm going to replace my v with my upper function. So I'm going to have the negative, because of the negative up front, we switch the order, 1 plus sine squared of x to the 10th. So I replace v with the sine of x. Now I have to multiply by the derivative of the inside function, being sine of x. So that's a cosine of x. Go to the next one, we have plus. Here we're going to replace 1 plus v squared to the 10th. We're going to replace the v with the cosine, so 1 plus cosine squared of x to the 10th times the derivative of what's inside. The derivative of cosine is negative sine, so let's just make this a negative here, sine of x. And that's all there is to it. Not that bad. Now, last one I want to look at and just set up for you at least is number 17. Here you have to take a couple derivatives. We have that capital F of x is equal to the integral from 1 to x of f of t dt, f of t dt. And we're told that f of t itself is actually an integral from 1 to t squared of the square root of 1 plus u to the 4th over u. We want to find f double prime of 2. We want to find capital F, that is, double prime of 2. Well, we've got a couple of things going on here. Big F is a function of x, but this function of x is actually a function of u. So let's see if we can take it one step at a time. Let's first of all find capital F prime of x. By the fundamental theorem of calculus, it's just little f of x. Everybody agree? We're just fundamental theorem of calculus, constant here, just a variable up here. So we're just going to take our function and replace the dummy variable of integration with the variable of our function, which in this case is x. Okay, so from here now we can find f double prime of x, which is equal to f prime of x. Now we're going to use the fundamental theorem of calculus here. So we're going to use the fundamental theorem of calculus to get, well, it's going to be a form of this, 1 plus t squared to the 4th over t squared times 2t. So I'm going to let you guys take it from there. You're going to take the derivative of this using the fundamental theorem of calculus and the chain rule, and then once you have that, you're going to take f double prime of 2, which will be the same as f prime of 2. And you're just going to put a 2 in wherever you see your variable t in this case. So I guess I said misspoke. It's a function of x, ultimately a function of t here. All right, so good luck with that. The password for your last homework assignment, 5.4, is it's inanition, I-N-A-N-I-T-I-O-N, which means, among other things, the absence of intellectual vitality, and hopefully we haven't lost too much of our intellectual vitality as we have gone through quite a bit of calculus in a relatively short amount of time. Inanition, INA, and ITION is your password. Good luck. As always, let me know if you have any questions.